I want you to start by picturing two very different things. On one side, hold an image in your mind of a rough, shiny, heavy nugget of metal. It feels ancient.
Right.
It's sitting in the palm of your hand, raw and unpolished. It's the kind of thing that sparks gold fever just by looking at it.
It's the classic treasure hunter's dream,
Yeah.
the visible reward.
Exactly. Now, on the other side, I want you to picture a massive industrial dredge. We are talking about a machine that is stories high, floating in a river, churning up the bottom with these enormous buckets.
Oh, yeah. It's loud, it's violent, and it's an absolute beast of modern engineering.
It is a striking contrast, isn't it? You have the sort of romantic allure of the natural material, the nugget.
And then you have the sheer industrial force required to actually get it on a global scale.
And that is exactly what we are diving into today, the dual nature of the gold industry. We're going to walk through a stack of research that takes us all the way from the first coins minted in ancient Turkey to the complex physics of fluidized beds. Basically, how did humanity go from, picking up shiny rocks in a stream to engineering ways to catch gold that is literally invisible to the naked eye?
It's really a journey of physics. Because the central problem, it hasn't changed in 5,000 years. Whether you are a Lydian king or a modern engineer, the question is the same. How do you separate the treasure from the trash when the treasure is hiding?
So let's unpack this, starting with treasure itself. Because looking at these notes, it turns out gold isn't always just, gold. The source material highlights a specific alloy called electrum.
Right.
Now, I've heard this word in fantasy novels, usually as a kind of magical currency. But what is it in the real world?
In the real world, electrum is a naturally occurring alloy. It's primarily gold and silver, just mashed together by geological forces deep underground.
So it's not just those two?
No, you often find trace amounts of copper, platinum, or even palladium in the mix. It's rarely found as pure 24-karat gold in nature.
And that composition actually changes the color, which is something I found fascinating in the data here.
Yeah, it really does. We have this cultural default that gold is, gold-colored. But electrum sits in this pale gold or sort of greenish-yellow range.
Yeah, the color spectrum chart here is really cool. You've got bright gold, which is your pure O. But as you slide down into the electrum range, it gets paler.
And if you go the other way and add a high copper content, you get brassy gold.
But the one that really caught my eye was green gold.
That is a really interesting one. Green gold is essentially the man-made equivalent of electrum. We can actually synthesize it today. Often, jewelers will deepen that greenish hue by alloying it with cadmium and gives it a very distinct look.
And speaking of man-made gold, here's a cocktail party fact I absolutely loved from the reading. The Nobel Prize medal. It's not solid gold.
It is not. The core is actually constructed of green gold synthesized electrum, and then it is plated with pure gold to give it that classic warm aesthetic.
No way.
So under the surface, the highest award in science is actually a tribute to this ancient alloy.
That is wild. I'll never look at a Nobel Prize photo the same way again. But let's go back in time. Historically, where was this stuff coming from? The sources keep pointing us to Turkey.
Specifically, the region of Anatolia. We call this the Lydian legacy. The research identifies the Pactolus River as the chief source of electrum in the ancient world.
And because of that river.
This region produced the very first metal coins in the Western world, way back around the 3rd millennium BC.
But the notes mention something a little suspicious about those coins, right?
This is where the detective work comes in. When geologists analyze natural Anatolian electrum from the river, it is typically 70 to 90% gold.
Okay.
But when we analyze those ancient Lydian coins, they often show a significantly lower gold content.
So the government was watering down the drinks.
Essentially, yes. It suggests the ancients were intentionally diluting the alloy during the smelting process to make the gold stretch further. It seems inflation and currency debasement are very old concepts.
Classic. But they weren't just making money. The Egyptians were using this stuff for architecture.
Correct. They utilized electrum as a durable exterior coating. Imagine the capstones of the pyramids or the tops of obelisks. They would be plated in this alloy.
Why electrum and not just pure gold?
It comes down to those physical properties. Electrum has high reflectivity and excellent corrosion resistance. It would shine like a beacon in the desert sun without tarnishing as quickly as, say, silver or copper. It was engineering as much as it was decoration.
Okay, so we have this amazing material. Ancient civilizations are obsessed with it, but now we have to get it out of the ground. And this is where the deep dive turns into a serious engineering challenge.
The fundamental principle at play here is gravity separation. It sounds simple, but the entire economic viability of a mine rests on one single variable: the density difference between the valuable metal and the worthless rock.
And the context here is huge. The sources say over 64% of California's historical gold production came from placer deposits. So we aren't talking about hard rock mining where you're tunneling into a mountain with dynamite.
No, no. Placer deposits are loose soil, sediment, and gravel, usually in riverbeds or ancient channels. You're just processing dirt. But here is the problem, and it is a massive one: colloidal gold.
Colloidal, that sounds small.
It's microscopic. In the industry, we call it flour gold or flood gold. It is so light and has such a high surface area relative to its mass that it tends to just wash away with the water you're using to separate it.
So it floats.
Effectively, yes. It acts more like part of the liquid than a solid rock. And the statistics here are sobering. Early mining methods lost 30 to 40% of the gold because they simply couldn't catch these finds.
Wow. Imagine throwing away 40% of your paycheck every month just because the coins were too small to pick up.
It's a huge loss. I mean, even as late as 1945, the recovery of free gold averaged only 70 to 75%. That means a quarter of the wealth was just flowing out the back of the machine and back into the ground.
So, to solve this, the industry developed a language of concentration. The sources break this down into a flow of 3 stages. Can you walk us through that?
Think of it like a funnel or a filter system. First, you have roughing. This is the initial upgrading stage where you just want to remove the bulk of the waste rocks.
Right.
You aren't worried about perfection yet. You just want to get rid of the big gravel and sand.
Okay, so you've dumped the big rocks, then comes cleaning.
Right. You take that concentrate from the roughing stage, which is now much richer in gold but still dirty, and you retreat it to remove more impurities. You're refining the product to get a higher grade.
And finally, scavenging, which sounds exactly like what it is.
It is the safety net. You go back and process the tailings, the waste, from the first 2 steps to see if you missed anything. But there is a trap here, described in the notes as the efficiency trade-off.
I'm looking at the graph for this in the source material. It shows 2 lines crossing each other. One is concentrate grade, and the other is total recovery.
And the key is that they work against each other. As you increase your processing intensity to get a purer grade of gold line A goes up, your total recovery often goes down line B.
Why is that?
Because to get the sample 99% pure, you have to be very aggressive in throwing out anything that looks like dirt. In doing so, you inevitably throw out some gold attached to dirt. So the goal isn't just purest gold, it's finding that optimal economic balance where the 2 lines intersect.
You want the most money, not necessarily the purest dust.
Exactly.
Let's talk about the tools they use to try to hit that balance. We start with the classics. The gold pan.
The oldest method in the book. It uses circular motion in water. It's iconic, but let's be honest. It has very low capacity. You can only process a pan at a time, and it requires a lot of skill to not wash the gold out with the dirt.
Then they scaled up to the rocker, or cradle.
Which is basically a box on wooden skids. You shovel material onto a screen on top, and you rock it back and forth like a baby's cradle. The rocking motion helps stratify the material, shaking the heavy stuff to the bottom.
But the real workhorse of the gold rush seems to be the sluice box.
An artificial channel. You divert a stream of water through a long wooden box, but the key component here is the riffles. These are obstacles, wooden slats or bars placed at the bottom of the box.
Like little speed bumps?
Ideally, yes. As the water rushes over them, they create turbulence, little eddies of swirling water behind the slat. This turbulence traps the heavy gold behind the riffle, while the water flows over the top, carrying the lighter dirt away.
It's simple, it's effective for big nuggets, and you can move a lot of dirt.
But remember, we are trying to catch the flour gold, the stuff that floats away. Sluices aren't great at that, so technology had to advance. Enter the intermediate tech. Shaking table.
Okay, now we're getting into something a bit more complex.
Now we're getting into differential motion. A shaking table is a large, flat surface that doesn't just vibrate randomly. It has a specific mechanical stroke. A slow forward stroke, and then a rapid return strike.
So it jerks back quickly.
Yes. And this causes the particles to actually crawl along the table. This leads to stratification. The finest, heaviest particles. The gold settled to the bottom behind very small riffles. The larger, lighter particles stay on top.
And then you add water flowing across it.
Right. Water flows across the table, washing away the light stuff on top, while the heavy gold crawls along the bottom to the collection point. If you ever see a video of this, it's mesmerizing. You see a distinct line of yellow gold separating from the black sand.
But what if you don't have water? The source material brings up the dry challenge, mining in places like Southeast California or the arid deserts of Australia.
Then you have to use air as your fluid. The dry washer is essentially a waterless sluice. Instead of a stream of water, it uses bellows to puff air up through a porous cloth bottom.
So it's blowing the dirt up.
It pulses it. The air pulses stratify the material. The gold, being heavy, settles down against the cloth behind the riffles, while the sand gets blown up and over the top.
And there's a more advanced version of this, the air table.
The Oliver gravity separator,
Yeah.
That uses the concept of fluidized beds, which we'll see as a recurring theme in advanced mining. Continuous air pressure keeps the lighter particles suspended, fluidized, so they flow downhill like a liquid. Meanwhile, vibration moves the heavy particles upslope.
So it's using air to mimic the physics of water.
Exactly.
Okay, moving to high volume. If you're a massive mining operation processing thousands of tons, you can't use a little shaking table. You need to move mountains. The sources mention static concentrators.
Specifically the Reichert cone. This thing is a beast. It is a stack of multiple inverted cone sluices, one on top of the other. The amazing thing. No moving parts.
None. No motors.
Gravity does all the work. The slurry flows down the cones, and the geometry forces the heavy material to the center. It has massive throughput. We're talking 75 tons per hour.
But there's a catch.
It is finicky. It's highly sensitive to fluctuations in feed density. You have to keep the mix between 55 and 70% solids. If the slurry gets too watery or too thick, the separation just stops working.
Okay, another static method mentioned is the pinched sluice.
Simple physics again. It is an inclined trough that narrows at the discharge end. As the slurry rushes towards that narrow exit, it crowds together. This deepens the bed and forces the heavy minerals to the bottom.
And then?
As it shoots out the end, a blade called a splitter literally slices off that bottom layer of rich concentrate.
I love how mechanical this is. It is just utilizing flow dynamics to sort atoms. Speaking of flow, let's talk spiral concentrators. I've seen these in photos. They look like big vertical corkscrews or slides at a water park.
They work on a combination of gravity and centrifugal force. As the water and sand spiral down the drain, so to speak, the speed increases. Centrifugal force pushes the fast, light material, the water and the sand, to the outside rim of the spiral.
Because they're moving faster.
Exactly. And the gold, being heavy, it drags along the bottom and moves slower. It stays near the inner column of the spiral. You have little ports near the center that just suck up that concentrate as it goes down.
Okay, here's where it gets really interesting for me. The physics of jigging. This section of the source material breaks down a single pulse of water into 4 distinct steps. It's not just shaking stuff up and down. It's a cycle.
It is a precise timeline. Let's walk through it. Step 1 is differential acceleration. You push water up through the bed of rocks. Now, Newton's laws kick in. Light particles accelerate faster than heavy ones. They shoot up higher.
Creating the initial separation.
Right. Then step 2 is hindered settling. The water stops pushing up, the bed of rock starts to fall back down. But because it's crowded, the heavy particles sink faster, pushing their way through the crowd of other rocks.
It's like a bowling ball falling through a pit of plastic balls.
Perfect analogy. Then step 3 is consolidation trickling. This is the suction stroke. The water sucks back down. This pulls the very small, heavy particles through the tiny gaps, the interstices between the larger rocks. They trickle down to the bottom collection area.
And step 4 is just rest.
Step 4 is the rest period before the next pulse. Modern jigs, like the sawtooth drive, actually modify this cycle to keep the bed open or expanded for longer, specifically to give that fine gold more time to trickle down.
It is amazing that we've broken it down to that level of detail milliseconds of a water pulse. But even jigs struggle with the really, really small stuff, the slimes.
Sub-100 micron particles. Standard gravity methods just fail here. The particles are so small they act more like part of the viscosity of the water than distinct rocks. They just float.
So what's the solution for the slimes?
Orbital motion, the Bartles-Mozley separator. Imagine suspended fiberglass decks that use a specific orbital shaking motion. This settles high-density particles out of a flowing film. It is effective down to 5 microns.
5 microns is basically dust. It's invisible.
It is barely there. But when you're processing millions of tons of ore, That dust adds up to millions of dollars.
But the heavy hitter for fine gold seems to be the Nelson concentrator. This is listed under advanced centrifugal.
This was a game changer. In a standard centrifuge, like a spinning salad spinner, the material just packs solid against the wall because of the G-force. You can't separate anything if it is a solid brick.
Right, it just sticks there.
The Nelson innovation was the fluidized bed again. It injects pressurized water through the wall of the cone, pushing back against the centrifugal force.
So the wall of the machine is porous.
Effectively, yes. This keeps the bed of gold alive, or fluidized. It allows the heavy gold to penetrate and displace the lighter rock without the material becoming compacted. It achieves recovery greater than 95%, catching gold as fine as 38 microns.
That is incredible precision.
Oh.
We've gone from shaking a wooden box in a creek to injecting pressurized water through a spinning cone wall against 60 Gs of force.
It is the evolution of engineering. But there's one more method in the sources, one that moves away from physics and into chemistry. Amalgamation.
This is the scary one, using mercury.
It utilizes the chemical affinity of mercury to bind with gold. When they touch, they create an amalgam, a physical bond. Miners would coat copper plates in mercury or put mercury in rotating barrels. The gold sticks to the mercury like a magnet and the dirt washes away.
But the risks box here is bright red for a reason.
Crucial warning. First, there's flowering. If you agitate the mercury too much, it breaks into microscopic beads. It doesn't catch the gold, it just escapes into the river.
And toxicity.
Extreme health and environmental hazards. Mercury is a potent neurotoxin. It doesn't degrade. This is why modern large-scale mining has moved away from mercury towards the advanced physics methods we just discussed, like the Nelson. We want to use gravity and force, not poison.
So looking at the big picture, the sources provide a strategic selection summary table. It really shows the evolution of the industry.
It does. It breaks down the battlefield. On one side, you have low-tech coarse. The target is nuggets, greater than 1 millimeter. You use sluices and jigs. Your goal, 60 to 70% recovery. The easy picking.
I'm on the other side.
High-tech finds. The target is slimes and flour, less than 100 microns. You use centrifugal concentrators and shaking tables. The goal is 95% plus. Total capture.
It is not just about digging anymore. It is about engineering efficiency.
The industry has shifted from a hunt for visible nuggets to the precise engineering of microscopic capture. We aren't looking for rocks anymore. We are looking for specific atoms.
Which brings up a provocative thought for me as we wrap this up. If the old methods only caught 60% of the gold, and we know where those old mines were.
You're thinking about the tailings.
Exactly. There are mountains of waste dirt sitting next to ancient mines in California, Turkey, everywhere. And if 40% of the gold is still on there because they couldn't catch the flour,
then those waste piles are actually gold mines. They're just waiting for modern physics to unlock them.
now that is something to think about next time you see a pile of dirt. Thanks for joining us on this deep dive into the shiny stuff.
Pleasure to be here.
Catch you next time.